Hello and welcome again. So in the last video, what we saw was the control of the AC-DC half-bridge converter. And what we did in that is that uh, instead of using or changing the modulation signal manually, that is our M, we were uh, generating the modulation signal using a PI controller. And so as a user, I was giving the reference value of the current that I want to flow from the terminal voltage or from the converter to the source side, and the PI controller was generating the desired M and generating that voltage drop across this RL so that our reference current could flow, right? So today what we'll see is that when we see the current that was flowing, so basically we were giving the I reference values from 0 to 1000 amperes, right? So it was following that I reference value, so it was 0 amperes, and at 5 seconds it was going to uh, the desired current, that is 1000 amperes. But if we see the initial transient, initially there is a huge transient, so basically there is a high negative current, and this current is flowing from the source to the converter, and it is of the magnitude 2.5 kiloamperes, and which is a huge current. And and in the system we really don't want this unnecessary transient. We don't really want to stress our converter, right? And so we need to find a mechanism so that this initial huge transient could be avoided, right? And if we see that the voltage that was getting generated at the output of at the terminal was was 400 initially. Well, it would be 400 because we didn't want any current to flow, and our source voltage was 400, so the drop would be zero and the current would be zero, right? So the voltage that we see was 400 volts, and afterwards it was increased a bit by the controller, and we were getting our desired current, right? And we can see that voltage at the output of the compensator or the PI controller. And that is also what mentioned in the book, is that this U is our terminal voltage. Basically the output of the compensator is the U. And what it says here is that when the gating signal are activated, the half bridge converter generates an AC side terminal voltage that is equal to the output of the compensator U, right? So U is our basically the terminal voltage, right? Since the system is initially in the zero state condition, U starts from zero. So the terminal, or so does the VT. So basically the VT starts from zero. So if we see the scope, see the output of this compensator as well as our measured terminal voltage, we see that, yeah, what we see here is that these voltages, the yellow one is the output of the compensator, and the blue one is our measured voltage, the terminal voltage. So it starts from 0 and goes up to 400, and then it follows our reference value of current, that is 0 amperes, right? So basically the output of this compensator is 0 initially, and that's why the system starts from a lower voltage, but our source voltage is pretty much 400 volts from the beginning itself, right? So there is the huge voltage drop between this the terminal and the source being at a higher voltage of 400 volts, and this starts from 0. That's why we see that the current initially has a very high amplitude, and it is in the negative direction, and it is 2.5 kiloamperes, and we don't really need this initial transient. So here what mechanism we would be using, as mentioned in the book as well, is that to avoid this, we will use the feed forward compensation. And this is basically a very very efficient and effective control concept, and it and there are various features and various advantages of it, and the book gives two or three advantages of using the feed forward compensation. So in this video we'll just see that the first advantage of using the feed forward compensation was to avoid the startup transient, the huge transient that we see in the current initially, that is unnecessarily stressing our converter initially. We don't really want that, and to avoid that we'll see that how we can just mitigate it, remove it using the feed forward compensation. So what we'll do is that the output of our compensator or the PID controller is our terminal voltage and it starts from 0, right? So we don't want that. So what we'll do is that, let me remove this, and we will basically put the information of the source to the output of the compensator. We'll add the the information of the source here, and that is basically our feed forward compensation. So if we see here that if the control scheme is augmented with a feed forward compensation, then we can remove that undesirable startup transient. And what we'll do is that initially we will give, so basically if from the starting itself our terminal voltage is 400 volts, then we'll have a zero current in the beginning itself, right? But we just saw that the output of the compensator starts from 0. So what we'll give is we'll add a block here, which is, let's take this one. So it takes the PI as well as we will give the source voltage. So this will take this one, VS, right? And we'll take a a P controller only, and we'll make it a proportional controller with gain of 1. So this is what it says in the book. So if you take a feed forward compensation with a transfer function of 1, basically it's a gain of 1, a proportional controller, then we can avoid that initial transient. So I just gave it a 1, and we'll put the 400 volts here and add it here, right? Let's see how it behaves now. So initially we see that the current was 2 to this, because there wasn't, the voltage at the terminal starts from 0, so the drop was negative. But now what you see is that the current starts from 0 and the initial transient has been avoided. There is an initial transient, which but this current is very negligible. We can neglect it, and our converter won't be stressed or uh, uh, get impacted or affected by this small amount of current. But that 2.5 kiloamperes was too much, so basically that transient has been avoided now, and this is what it says in the book as well. So it starts from 0, and we can see in the book as well that there is some initial negative current, but not of the range of not in the range of kiloamperes, 2000 or 3000 amperes, right? And therefore, like what it says, that initially the voltage that we see, let's see the let's see the terminal voltage once. Yeah, yes. So the terminal voltage starts from it starts from 400 volts, and let's see, yeah, let's see if we just put a gain block here. Yeah, 1. What happens then? So it would also work, and the terminal voltage starts from 400 volts, and we don't get that initial transient. So this is one of the advantages of using the feed forward compensation, and this is how it looks, then the updated block diagram. And in the next video we'll see the other advantage, which is basically decoupling the AC and the converter system. So basically, if there's a AC system, a proper AC system will replace the source with the AC system, and there would be some oscillations in the current, in the voltage that we'll see, and that's going to impact the terminal voltage as well as the output current of the converter. But with a feed forward compensator, we'll see that if we give the control the information of the AC system, and feeding it to the control in the initially uh, in the initial stage, then we can avoid those oscillatory oscillations in the output, oscillations in the voltages and currents of the system. So that's it for this video, and do subscribe and like the video if you learned something from it, and we'll continue to make videos, further videos on the book, following this book, right? So thank you.